Okay, guys, we're continuing with the next talk. Since we are already a little over time, I directly give the word to Travis Goodspeed, who is going to talk about reversing and exploiting wireless sensing. Please.
Can everyone... Testing? Hello? Okay. It's really hot up here. If someone would grab me a club mate, I would appreciate it. Or beer, depending upon how you want the lecture to go. So today I'm going to speak about reversing and exploiting wireless sensors locally. A wireless sensor is a very small computer which is able to survive in the field running wirelessly from battery power for very long periods of time. So while your laptop might last for a couple of hours on battery power, a wireless sensor is designed to run for months or even years. And in doing this, it can send you back. Could we turn it down just a bit for the feedback? Or could you turn the volume down just a bit? Great. So as these things are in the field, they're very cheap, and you place a lot of them. In the case of the smart electric meters that are being placed out in the American electric grid, 5 million of these things have been deployed. And for security, they often rely upon hardware-accelerated cryptography that occurs within each device. Well, that might work fine when you have servers held in defended castles. But it doesn't work very well when you have wireless sensors out in the field that can easily be captured by an attacker. So in the case of the electric grid, if you steal one... beer. You're in for a treat.
First things first.
Yes. So having captured a single wireless sensor, it's worth considering how you might move that into a larger exploit. Like if you capture one node of a network, can you extract its credentials and then speak to the rest of the network, exploiting them wirelessly using network attacks and stuff that are familiar to you from, say, IT security or things like that. So I'll discuss schematic capture. Given a captured device, you want to be able to figure out which wires contain which signals. And you want to be able to do this as quickly as possible. And thanks to the hardware-accelerated I/O ports of the chips used, you can be guaranteed that the particular functions will run over particular pins of each chip. We'll also discuss the protocols that are used to send data from one chip on a board to another, and how you can wiretap that line of communication, that internal serial bus, in the same way that you might wiretap a network using a packet capture device. We'll discuss how to extract and dump firmware. So having captured this device, you want a copy of its programming. Unlike in the PC world, where you can just purchase or download whatever software you wish to attack, in this space, you very often have to extract it from a functioning device which has had, say, a fuse blown to protect you from, or to protect the device from you extracting its firmware. We'll also discuss simulation and the reverse engineering of firmware. So if you wind up with an application intended for a very rare chip, how do you write the tools to take that chip apart? How do you simulate the software to test for vulnerabilities virtually rather than having to crash and restart a physical unit? And we'll conclude with some observations about how to fuzz microcontrollers. So a wireless sensor itself is built up of a 16-bit microcontroller. And this contains within it all of the traditional parts of a computer. You have RAM, you have ROM, you have flash memory, sometimes you have EEPROM. And these are held within a single package, so it's very difficult to spy on what one piece of the chip says to another piece of the chip. We'll also, and then they also have a radio, such as a ChipCon 2420 or 2500, which allows it to send a wireless broadcast over a very short range. In the wireless sensor networking model, you have a mesh network of, say, 100 sensors, each of which is also doing mesh routing. And then you have sensors or actuators or something to use as input and output to make the device actually useful. And that's beyond our discussion today, because I'm telling you how to break these things, not how to run your business on them. And then they'll have serial ports for debugging. So the MSP430 is a von Neumann chip with hard fuses and a masked ROM bootloader, which means that when you capture this chip, there's an actual wire in it that breaks to secure it. And this locks you out of the JTAG port. So the other routes in are through attacking software or through attacking the bootloader. And in certain versions of the bootloader, I found a timing attack, which you might remember me presenting at the Congress in December, which allows you to guess the password 1 byte at a time. For every guess of the password you make on these vulnerable chips, the password comparison takes 2 clock cycles longer. So you can run your password, measure the amount of time, and then if you send your traffic in the correct weird way, the difference between your beginning the broadcast and getting back a non-acknowledgement telling you that your password is wrong reveals the password. This is in contrast to the AVR, which is a Harvard architecture chip. So you actually have 2 separate memories, one being flash ROM and the other being RAM. And a pointer might refer to one or the other. The only thing that specifies that is which instruction you use. And these are exploited differently. You can't write a simple Stack Overflow exploit for the AVR because you can't execute RAM. But on the MSP430, it's just as easy as in those mid-90s articles on writing Stack Overflow exploits. You just overflow the return pointer and you make the return value a piece of RAM. Further, the incoming packet is always stored at the same address, so you can be rather certain of where you should jump. Now, to figure out a schematic diagram, suppose that you've got an MSP430 1611 and a ChipCon 2420, and you want to know which pins connect them. This arrow is actually in the wrong place, but the theory holds. These 2 pins are what connect to the host PC. You know this because they are URXD0. That means the universal asynchronous serial port receiving pin 0. And then up here you see SIMO, SOMI. These are the pins for synchronous serial, which is how the radio speaks to the microcontroller. So there's actually a clock edge, and on every rising edge, the master writes 1 bit to the slave, and the slave writes 1 bit to the master. And then on every falling edge,